Hi everyone, and welcome back. We talked in part 6, if you remember, about continuous improvement. And let me start saying something here. If continuous improvement has two legs, these are corrective action and preventive action. And if you remember, we mentioned there that in order to verify the effectiveness of these actions, we have to assure the complete elimination of the root causes. And finally, for both types of actions, whether preventive or corrective, the real effectiveness of these actions shall be always evaluated based on the complete elimination of the root causes. And in this case, we shall be careful that treating only the symptoms of the problems without taking out the problem tree from its deep roots will not guarantee that the same will not grow again. So we need always to find the roots of the problem or the potential problem, the risk, and make sure of their complete removal. So this is why the topic of today is very important. So we cannot just look at the exposed part of the iceberg. We have to go below the surface of the water and dive deep until we arrive to the real root cause. From the name, it's root. Then we have to dig deep and deep. So be prepared for the deep dive. And usually when we are diving really in the sea, we are preparing ourselves for the surprises that we can see while exploring the marine life. So don't get surprised when we are digging into this topic, that is a very important topic. You may see that we are going to deal with so many quality terms and techniques that we have already explained or that we will explain in the future that has to do with the root cause investigation. Then we'll go through many topics, as I mentioned: process approach, process variation, the normal one, the special cause one, reliability, plan, do, check, act, risk-based thinking like failure mode and effect analysis, many techniques that are interacting with root cause investigation, as I mentioned, because it's in the heart of the quality. Something to add here, I just remember this after the exercise really, that why this topic really is sensitive. People try to avoid a root cause investigation, an effective one, and to dig deep into the root of the problem simply because the deeper you dig, the more costly causes you may find that can be systematic, and also the more hierarchy level you may arrive. This is why people tend to, in many organizations, tend to blame somebody around the problem rather than doing an effective root cause investigation. This is why this topic is important and is sensitive. Let's start. Well, let's agree that the purpose of any root cause analysis is to find effective solutions to problems such that they do not reoccur. Root cause analysis can be defined as an investigative data-driven approach to determine the foundation of problems and consequently inform where solutions might be found. So simply, it's an investigative data-driven process where both research and analysis are needed to define the problem, understand the causal mechanism underlying transition from desirable to undesirable condition, and to identify the root cause of the problem in order to keep the problem from reoccurring by using a structured procedure. But let us first, in this introduction part, answer the question, when do we need to do root cause investigation? Actually, it is very important to answer this question first before we dive into this topic. Since the way some companies or clients or even third-party auditors dealing with all types of quality problems equally and asking always for root cause investigation and related corrective actions without differentiating between those cases of detected nonconformities or nonconforming products that require RCI and the cases that do not require that, still of course require correction and containment actions as applicable. And this mixing in concept is leading sometimes to enforce some companies to generate inaccurate or general RCI statement or record for every non-conforming product produced, every rejection, even if this rejection is part of normal process variation and expected margin of NC products resulting from such process as per its capability. Now, this impractical approach and unnecessary demand can lead that this critical process, which is a key for improvement, become a bureaucratic formality of records generation and archiving that quality people have to do just to pass audits, reminding us of what was mentioned in last part about quality guy as the paper guy. And this will unfortunately contribute to the wrong perception about quality people mentioned in last part about being impractically demanding. ending with what we see today in some companies where RCI process is not taken seriously, even for cases that really require an effective RCI, and hence we see root causes like human error, operator mistake, machine malfunction, system glitch, etc., that are basically excuses more than causes, since even if these are general description of what happened, but they are not really telling why that happened. And this is why we need first to define those quality problems that need RCI. Okay, now quality problems or the quality failures, as per the terms used in last part, that require RCI can be either external failures or internal failures. And let us start talking about external failures, as of course it's more critical, especially if product is impacted. And quality external failures is usually either related to a deviation from specified requirement of a product or a process, or from any other quality contractual requirement detected externally. So basically deviation from any specified requirement, as mentioned in part 1, when we define equality from manufacturer perspective as
from
meeting
manufacturer
specified
service provider
requirements.
perspective, quality means mainly meeting specified requirements.
The second case, which is more serious, external quality failure, is when we deliver a non-conforming product to the client with questionable quality and consequently questionable reliability. And here we have actually two problems that require to be investigated for their root causes and not one problem. The first is why the non-conforming product was there, so the root cause of the problem. The second is why our system failed to detect the problem or the non-conforming product before delivery, so the root cause of not detecting the problem. Okay, now the internal quality failures or problems detected internally by our system that require to investigate their root causes are either one of the following two main types. First type is the typical non-compliance or a deviation from a specified requirement, which can be a standard requirement, an internal procedure requirement, or from a client contractual requirement. So basically, again, deviation from any specified requirement. And this is a quite clear and straightforward problem. Now, the second type of internal quality problem which require root cause investigation is when we have non-conforming products produced abnormally due to process uncontrolled variation. And this can be mainly two types. The first type is the special cause abnormal variation, and the second type is applicable for processes that require validation like welding and heat treatment, when we are working out of the qualified limits of the essential variables of these processes in uncontrolled way. Well, but why this type of product rejection due to such variation shall be considered a quality problem which require RCI? Why not just rely on inspection and sort the good from the bad, since as said, any process has some variation and some percentage of products will be normally rejected. So where is the problem here that require RCI? Well, let's try to clarify this first, as it is important to tell what is normal and what is abnormal when we deal with rejection and process variations, which is an important topic in quality, and this is why we made this introduction before entering in the main topic of root cause investigation. Okay, now as per international standards for tubular products in oil and gas sector like API and ISO standards, there are tests that are required to be conducted 100% on our products on each pipe as required by such codes to assure product integrity against certain serious types of defects like cracks, pinholes, deep gouge, etc., or critical dimensions like pipe internal diameter for casing and tubing, since otherwise having such defects or dimensional issues in our products can result in relevant impact on reliability of such products for the intended services with all related possible consequences. So these standards and applying risk-based inspection concept mandate, for example, 100% hydrotesting of our pipes, which is a proof test, 100% ultrasonic, which is an NDT test, and 100% drift test apart from other 100% test inspection like weight and length measurements, etc., etc. While on the other hand, there are other quality parameters and characteristics of the product that cannot be practically inspected 100% as quality control. due to the extremely high cost and high impact on productivity, or maybe due to the destructive nature of these tests, like mechanical testing, for example. Hence, for such parameters and properties, we do only sample inspection and testing and not 100%. Then, how can we assure that quality of such products is okay to be released to the client without inspection of these parameters? Well, this is based on process control. And as mentioned before, this is a prevention approach in which we have to assure quality assurance having a standardized and consistent process, which is following a general logical assumption that repeating exactly the same process activities using the similar raw material by the similar qualified and educated resources and controls will result in giving the same target output product, that is QA. And of course, we can only validate this assumption by taking some samples of the process output, the products, and checking them for such features and characteristics at start and then on certain frequency, which is QC, which will assure also if the process remains consistent throughout production. So here we rely on process consistency, QA, mainly, and on this periodical inspection done for certain frequency or sampling plan of products, which is QC. Okay, but how can we decide such sampling plan? Whether we will check 20% or 10% or 5%, etc. Well, such sampling plan or testing frequency are either specified by the applicable standards as a minimum or decided by the production facility based on different factors. And these factors shall ideally take into consideration parameters like total population of products, target quality confidence level, and confidence interval. Now, quality confidence level of our products is simply a probability statistical term for, simply speaking, how willing we are to be wrong or to be correct. Like with 95% confidence level, we have 5% chance of being wrong or 95% of being correct. While the confidence interval is actually the allowable variation in the inspected parameter, or what we call in quality acceptance criteria range. And to link the confidence level with the confidence interval, we can say simply that when we have a 95% confidence level, it means that we have a 95% chance that our product's population readings mean, the mathematical mean of our readings, will fall between the lower limit and the upper limit that are usually the acceptance range defined by the standard or the allowable margin of error from the nominal target value. So, based on these parameters, we can calculate approximately the suitable minimum sample size which will achieve statistically the target quality confidence. Of course, this sample frequency is directly proportional to the target quality confidence level, which means if we want to increase the confidence level, we have to increase the inspection frequency. Now, this is expressed in terms of Z scores, and here you can see this Z scores for the most common confidence levels. But sample size is inversely proportional to the confidence interval, the allowable margin of error. So if we increase the quality confidence target from 95 to 99, we have to increase inspection frequency. But if we increase the allowable margin of error, or the acceptance criteria range, then we can reduce the sample size. However, and as mentioned in last part, when process control becomes questionable due to lack of standardization or due to process inconsistency, this will result in uncontrolled variations in the process output and possibly on our product's parameters. Then the only way now to assure the quality of our product is to increase inspection frequency, in some cases up to 100%. And as mentioned in last part, this increase in inspection, QC, is needed to compensate the weak process control and to try to maintain certain level of quality confidence in our products. And since we cannot maintain this 100% inspection as explained, but we cannot also reduce that due to the mentioned risks, then this is a quality problem for which we need to do RCI in order to detect and eliminate the root cause of this uncontrolled variation in the production process, or what is called special cause variation. Now for the second type of rejection due to uncontrolled variation of the qualified limits, and this is in the case of qualified processes like welding and heat treatment. Now these processes by definition as per applicable standards rely more on process control than quality control, since the only testing that can prove their effectiveness to deliver the target output is a destructive testing, which is in addition to the high cost and the impossibility to be done in high frequency, is time consuming and is giving late feedback after possible accumulated rejection. Hence, such processes require validation and have to go through a qualification stage before normal production can start. Now, in this qualification process, the effective working range of its essential parameters, the important one, is defined through a closed setup and monitor and through a detailed and intensive testing to assure that within such range, the target mechanical properties are guaranteed. Of course, with maintaining also other inputs, resources, and controls consistent. Now to clarify this further, let's talk about specific process which require qualification, like heat treatment process as an example. And heat treatment process, simply speaking, is a process of heating the material up to certain temperature and keep the material at this temperature for a certain period of time and then cooling down at certain cooling rate in order to achieve certain phase transformation, microstructure, and morphology that will generate certain mechanical properties, which is our target from this process. Now, for example, an essential variable for heat treatment process is heating temperature. So once the process limits of this variable are defined and validated through testing to deliver the target properties, we need now to maintain the same range throughout the production process after validation to assure that the output of this process is consistent. So in this case, anytime such processes start operating out of its validated qualified range of any essential variable like temperature in this case, in uncontrolled way, like reaching above the maximum qualified limit, we shall consider that this is a problem. But we shall consider that only if there is no systematic approach to deal with this increase. So it is uncontrolled. Otherwise, if we systematically identify the affected material with predefined disposition and fix the process to return back within qualified range, or we requalify the new range as applicable and feasible, then it shall not be considered a problem requiring RCI. But now, back to the topic of process variation and to try to understand further what is the difference between normal process variation and special cause variation, and how they are linked to process capability. And what is actually meant by process capability? Well, the main idea of process capability measurement is to give a projection of how many non-conforming or conforming products such process can produce in future according to its capability. And then when the process variation is between its upper and lower control limits for the extent expected as per its calculated capability as shown in these examples of control charts, then such variation is considered normal. While when variation is outside these limits and we are getting more non-conforming product than expected, then this is considered a special cause variation and shall trigger RCI process. And this is why, as mentioned, having a non-conforming product, if it is within such predicted rejection as per process capability, shall not trigger a root cause investigation and is considered normal. Of course, again, it needs correction and containment actions as applicable. But no RCI or corrective actions are needed in this case. However, one thing important to understand here, that all techniques used to analyze the process capability are assuming that process is statistically in controlled status. So we have what is called Process Potential Capability Index, CP, or Process Capability Index, CPK, with main difference that CPK consider actual process data centrality against the target specification range, while CP does not consider that. However, if the overall average is in the center of the specification, the CP and CPK values will be the same as per the following. But again, both indices assume that process is statistically consistent, which means simply that it is statistically systematic and predictable. And this is actually require some assumptions that process inputs like raw material are not varying, and that resources like operators and machines are not varying, and that measurements and other controls are very consistent with no or minimum uncertainties. However, and since for many processes in industry these assumptions are not accurate and we usually have some variations in input, in resources, and in controls, and many processes are not statistically consistent, so we cannot apply process capability studies in predicting probable future rejection for such processes. But of course, this does not mean that these processes are not in control. Well, I guess that this is becoming little confusing now because we said that the processes are not statistically consistent, but still they are in control. Well, let us first then define what is meant by control. Control is anything in your process that might prevent or detect the failure. Now, these controls, as mentioned in Part 7, are either process controls or quality controls. So, process controls are those controls that were preset to prevent failures by mitigating the potential risks of failure in a process and keeping the process in control between the predefined limits as much as possible. And quality controls are those controls that detect the failure early enough within the same process or in the next processes in order to avoid external failure and all related consequences. Now, these both controls, process control and quality control, should be ideally part of any quality control plan. But how these controls are defined? Well, each process has a target output, and these controls shall be effective enough firstly to achieve that output, which is process control, and secondly, in case of failure to achieve that, they shall be able to detect the non-conforming output early enough to do the needed sorting and correction, which is quality control. So for example, if we take process like pipe cutting process, so here we have a target to achieve certain length. Hence, during quality planning stage of this process, we define the following controls. Firstly, the process controls like length setting in the automation system, length sensor setup, cutting machine parameters adjustments, etc., in order to achieve the target length without failure, prevention cost. And secondly, the quality controls at the end of the process by mainly checking the output pipe length to assure compliance with target length tolerance, which is appraisal cost. Okay, now as a conclusion and back to our important point, to differentiate in simple way the uncontrolled variation from the normal one, when we detect non-conforming products during production, whether based on sampling or based on 100% inspection, we need to ask the following two important questions. First question, is that process introduced the detected product is under control, whether statistical control or process control as just defined? And this is part of normal variation. If the answer is yes, no need for RCI. If the answer is no, we need RCI. Now the other question we shall ask, considering the existing inspection frequency, quality control, are we having the risk of releasing NC product from the non-inspected part due to such process variation? So if the answer is yes, then we need RCI. Of course, we need also to consider the size of the problem and the impacted products, and to analyze the need for increasing the inspection frequency until process is back under normal control. Now the systematic way of determining such process and quality controls during planning stage is by applying process failure mode and effect analysis approach. But what is process failure mode and effect analysis? Actually, FMEA, as explained in Part 5, is a risk-based thinking approach in which we anticipate and evaluate the risks of failures in achieving the target process output in case of process FMEA, PFMEA, or the failure modes of a product in the intended service due to probable design errors, as was explained in Part 4 about reliability issues, which is design FMEA, DFMEA. So, in summary, DFMEA is answering the question what can go wrong in the product design to achieve the target characteristics and performance properties, product reliability. And PFMEA is answering the question what can go wrong in the manufacturing process of that product in achieving the predefined requirements and parameters, process reliability and consistency. And here, as manufacturers of product for oil and gas sector, we mostly don't really design new products since we are basically following international and client product specifications or certain patent specifications. So among the 3 stages that were mentioned in part 4 regarding product reliability that need to be considered for risks of failures, and that are design stage, manufacturing process stage, and service stage, our focus here shall be on the manufacturing process, or PFMEA, through which we are defining the controls, both prevention and detection of a manufacturing process, considering all failure modes and all things that can go wrong during the process, causing product to be out of the target requirements. And the main output of PFMEA process is to find those failure modes that have high risk priority number, RPN, in order to mitigate them by redesigning the process or adding some new controls into the process. But how is this PFMEA output can help us in RCI process? Well, reviewing such risks already identified before during PFMEA, even if they were with low RPN, can be a very useful start of the root cause investigation process, since it is possible that the failure under investigation has been already highlighted before with identified causes, which will save us a lot of efforts and time searching for root causes. Instead, we start working on corrective actions. On the other hand, and since such previously identified risk, possibly with low RPN based on some assumptions that were done at that stage, became already a problem now and not anymore risk, then we have now to modify its RPN as probability is confirmed to be higher than previous assumption. And accordingly, PFMEA output shall be revised taking into consideration the agreed corrective actions that will avoid the reoccurring of the same failure in future. And it is not secret that one of the assumptions that people do while doing process FMEA is that process inputs like raw material, for example, is very consistent and does not vary a lot. This assumption, of course, is considering that all controls apply the raw materials procurement process, starting from controlling and monitoring of vendor performance up to receiving inspection of such materials, etc., are well established and implemented consistently. This assumption might need, after some failures, to be re-evaluated, of course depending on the specific scenario and process involved. And sometimes it might be that the whole company risk policy shall be reviewed either to revise assumptions or to redefine acceptable risks level. Finally, in next part, we will continue this topic by explaining further the main techniques used in root cause investigation in industry and the minimum requirements of any RCI method in general to be considered effective to reach the root causes of a quality problem. Now, and after this long introduction about normal and abnormal process variations, and for those interested in statistical quality control, I have one open question for them. Please check and search and explore different ideas regarding those cases where our process is not really considered statistically controlled process, but still consider a controlled process as explained here. So can you think of a methodology using actually some statistical approach to decide for such processes if rejection of these processes is normal or abnormal? Of course, if it is abnormal, it will need to be fixed and require RCI. So please try to think and search for a practical approach. And I am glad to share with you that I have personally already developed one continuous improvement method combining different existing tools and approaches in quite a new way, and I have validated this practically for years and found it very practical and effective to define normal rejection from abnormal rejection. However, to be more effective, it needs to be further integrated with existing automation systems of industrial operations. But really, I believe that this topic worth more research and development, and I can assure you that in the real world, in industry, we need more creative but still practical and realistic methodologies, since unfortunately we have many ideal statistical methodologies that simply cannot be applied practically in our reality, which is not ideal. If you find this video useful, leave a comment, share this video, and subscribe to the channel for other people to know about it. Thanks a lot.